All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. This video is about putting numbers into bases. Typically, we're interested in rendering numbers that are already in decimal form into a base, like 2, so we can get binary numbers, 8, so we can get octal numbers, 16, so we can get hexadecimal numbers. What we need to remember is that each of these is just a way of expressing a number in a particular form that is convenient for us for a particular purpose. The number is a thing in itself, okay? And these different ways of representing them, these different bases, are akin to saying the word in a different language. Like dog in Spanish is perro, and so, but a dog is still a dog. It's not a different thing because you call it by a different name. It's just that you can speak about it in a different way. So anyway, let's get down to the nuts and bolts on this. Okay, so we're going to start off here. We have a number n that is greater than 0 and a number b that is greater than 1, and they're both integers. Okay. Suppose that n is equal to a sub n times b to the nth plus a sub n minus 1 times b to the n minus 1, etc. Down to a1 times b plus a0, where our ai's are all positive numbers, or at least non-negative numbers, and none of them is as big as b. We say that we have n rendered into base b. Okay, so this is what it is. Now, typically, you've seen numbers rendered into bases before. I mean, we work with base 10 numbers, and so you know what a number rendered into base 10 looks like. It's just a number that you've written down. We're interested in rendering into binary, okay, where the value of b is equal to 2. And so in that case, our a's are either going to be 0 or 1. We could also be interested in b equal to 8. That would give us something called octal numbers. A lot of people represent colors on a computer in terms of octal numbers. And b equal to 16 is common. That's hexadecimal. There are some folks who played around with rendering numbers into base 12. That's called duodecimal. And so typically, whereas b can be any positive integer greater than 1, typically 2 or 8 or 12 or 16, or most commonly, of course, 10. Okay, so let's say we have n that can be rendered into base b, and let's look at it like this. So we can have the a0 off to the side. Every other term has a common term, a common factor of b, so we can factor that b out, and so we have this number here, okay, times b plus a sub 0. Now, this is just a form of the division algorithm where n is divided by b. Okay, I'm assuming you're familiar with the division algorithm. I have another video on it in this series. You can go back and find it if you like. If I remember, I'll put a link to it in the video description. But I want to take this opportunity to define a little notation. So let's have some integers, p that are greater than 0, q greater than 0, d also greater than 0. But let's say, well, actually d could be equal to 0. We'll see. But we'll also have an r, which is going to be non-negative, but it's going to be less than q, right? So basically, this is just also the division algorithm right here. I put this because I want to define some notation. D is going to be P double division Q. That double slash sign stands for integer division. You divide and you get take the integer part, which is what we're doing here. I'm copying the Python notation on it. And R is read as P mod Q. Okay, so again, the assumption here is that we're dividing by Q, and we set up this notation so that we can state what we need to state a little bit easier. And so let's look here. We start off this divisor, okay, right here. What we the b times that. Well, we're going to refer to this number in parentheses as as n0. So we have our n0 right there, and so our n0 is just our n integer divide b. Okay. And my A0 right here at the end, right, is n mod b. Okay, so this sets up a procedure. Okay, so if we take have any integer k greater than or equal to 0, we can get n sub k plus 1 to be n sub k divided by, integer division by b. And then in this case, notice that my a sub k plus 1 is equal to n sub k mod b. Okay, so I can get, basically it boils down to the fact I can recover my digits, okay, in this base by doing this process. I'm going to work an example for you on this. Okay, what I've done is I've used the algorithm to take the number 143 and to put it into base 8. You start out, 143 is 17 times 8 plus 7. So we bring the 7 across. 17 is 2 times 8 plus 1. Okay. We bring the 2 across. 2 is 0 times 8 plus 2. And so we stop here because we have a 0 in that spot. We've finally gotten our n value to be down less than 8. That means that representing 143 as octal would be 2 times 8 squared plus 1 times 8 plus 7. So we would write this down as 217 octal. Okay. Is this right? Well, let's see. Okay. 2 times 8 squared, well, 8 squared is 64 plus 1 times 8, that's 8 plus 7. 2 times 64 is 128 plus 8 plus 7. Okay, so this would be, okay, addition. Addition is hard. 136 plus 7, and that is 143. Okay, and so yes, it works. Okay, so here you might come into a little feeling of deja vu because it's looking like we're just doing the same thing all over again, and in some sense that's true. But what I began this lecture with the presumption that we had an integer that was expressible in a particular base. And the thing is, that is an assumption. Given any base, do you know that you can represent any number in that base? Okay. And so what I have here, I'm setting up the algorithm, and I'm being a little bit more formal. I start out with a sequence of n's. I'll let n sub 0 be n integer divided by b, and I will then proceed recursively defining n sub k plus 1 to be n sub k integer divided by b. And so note that, I mean, we're dividing now by a number that is bigger than 1, and so at every stage these numbers are getting smaller. The n's will have to get smaller. That means that the n's, there must be some n sub n that will be equal to 0, and we'll just, when we hit a 0, we'll stop there. Okay. Now we define a sub 0 equal to n mod b, and define a sub k plus 1 to be n sub k mod b. All right, so we can get our n sequence of n's first, and then we can get our sequence of a's. Okay, now take that, and we can stack them like this. Okay, till we get down to our n sub 0, n naught, n sub n being equal to 0. Okay, now what you do at this point in order to prove that this works is just a little algebra. I know your math teachers are always saying, just a little algebra. Well, asking, is there anything such as big algebra? Well, yes, there is big algebra. This is not it. And just back substitute, okay, where these are stacked on top of each other. In the previous one where I have n sub n minus 1, just take this and substitute it in. And keep doing that. Each time you'll be gaining another factor of b, and when you do, it'll roll out into what we have here, that our original n is equal to this. And so our algorithm works. It will always work for any b. And so this will take care of putting integers into a base. Putting fractions into a base is slightly different. I may cover that in another video. Well, I hope you enjoyed this video and found it useful. If you did, please like it and subscribe. Thank you very much. Yeah, who is it? No, I'm not doing anything. Come on in.